Bismillahirrahmanirrahim. Assalamu alaikum. Our today's topic is about power factor. In electrical engineering, a power factor of an AC power system is defined as it is the ratio between real power to the apparent power. Power factor is an expression of energy efficiency, how effectively power is being utilized. For example, we say power factor is 0.8. It means 80% of the power is being used effectively. It is usually expressed as a percentage. Lower the percentage, the less efficient power usage is. In AC power system, the power factor is a very important parameter that defines how efficiently electrical power is being utilized by the load. Power factor of a system depends on the type of the load present, whether resistive, capacitive, or inductive. As we all know, there are three primary elements in electrical technology, that is, they are the resistors, capacitors, and inductors. As we all know, when the energy flows from source to load, in this process, four things happen to the energy. Number one, it can get lost. It is not available to the load. It is dissipated in resistor. Number two, energy can get stored. It can get stored in the two ways. It can get stored as a kinetic energy in the inductors. It can get stored as a potential energy in the capacitor. Number four, it can get transformed from one form to another form. We can say from electrical energy to the heat energy, or from electrical energy to the mechanical energy, etc. So generally energy either get lost or dissipated, or it can get stored. Therefore, there are three types of the loads: pure resistance, pure inductance, or pure capacitance. So these three are the basics to understand the concept of a power factor. So let us see. First we consider the following circuit. It is a simple circuit with a voltage source and also consists of a resistance. So we can call this as a resistive load. You can see there is a current I is flowing in the circuit. Let me ask a question. For a sinusoidal voltage wave shape, what will be the current wave shape under steady state condition? So let us look at that. On the x-axis there is a time, and while on the y-axis it is for the amplitude. The black curve is for the voltage wave shape, which is sinusoidal, and that is the source voltage as well. While the red curve, as you see, is the current wave shape. So for a resistive load, that is simple. The current is always in phase with the voltage in the resistive load. You can see. Now we shall apply a process. We shall multiply the voltage waveform to the current waveform for a pure resistive load. So by multiplying, we get the power waveform. You can see the power waveform. By multiplication, you can see there is one more waveform is added, shown in blue color, obtained by multiplying the current and the voltage instant by instant. Power starts from the zero and gradually rises up. When the voltage and current are zero, power is also 0. But when both voltage and current are in negative, product of that is still positive. Therefore, power waveform continues to rise up and become positive. Power waveform has no negative component. It has a frequency double than the current and the voltage waveform as shown. Now, what is the average value of the power? In the new figure, we remove the voltage and the current waveform, just keep the power waveform and the average value of the power. So we can conclude that we have a finite average value of a power as shown in thick blue line in the graph. So we can say there is a finite average power in pure resistive load. Now we will consider the inductive load. The circuit is shown. In this circuit, we have removed the resistance with inductor. The current is lagging the voltage waveform, as you can see. So in inductive circuit, we can say that the current is lagging the voltage. We are going to now in the next we are going to apply the same process. The voltage and the current waveforms, we are going to multiply the voltage and current waveform. When we will multiply, what happens? You can see much difference from the resistive load or the much difference from the resistive load or the resistive load waveform. Here you can see at origin angle 0, voltage is also 0, but the value of the current is in negative side because it is lagging. So the product or the power is 0 because voltage is 0. So power starts going negative, voltage is positive and current is negative. Therefore the product has to be the negative. So in short, power is negative and positive. You can see power is on the negative side as well and power is on the positive side as well. So what will be the average power in that case? You can see the graph by removing the voltage and the current waveform and just keep the power waveform. Average power value is exactly 0 for a true inductive load. So remember, for a pure resistive load, there is a finite value, or we can say there is a finite average value. This is the crucial difference between the two. In the case of inductive load, there is a no average value for the power. Now our third basic component is capacitor. So now we will see the capacitive load. Now consider the capacitive load. Here we have removed the inductor with capacitor. Now what will happen for the current wave shape? In this case, the current is leading the voltage. So we can say in capacitive circuit, current is leading the voltage. So again we are going to apply the same process as we did with the resistive set and inductive set. we are going to multiply the voltage waveform and current waveform. By multiplying the product, we can get as power. In short, we can say the power is also in a negative and positive as shown. So what will be the average power? The graph, by removing the voltage and the current waveform and just keep the power waveform, average power value is exactly 0 for a true capacitive load. This is remember, for the pure resistive load there is a finite value, or we can say there is average value, but for capacitive or inductive load the net average value is 0. So this is the crucial difference between inductive, capacitive and resistive load. Average power is 0 in pure capacitive load. Now we are going to draw the comparison of all three loads. The resistive load, inductive load and capacitive load. You can see there is a finite or non-zero average power in case of a resistive load. You can see the zero average value for the power in case of a inductive load and in case of capacitive load. Resistive load, there is a finite average power, that is called the real power. The average power is absolutely 0 in case of inductive or capacitive load. So we can say in pure AC resistive circuit, voltage and current are in phase. All the power entering the load is consumed. So this is what is real power. But when we have reactive loads in capacitor or inductor, energy stored in the loads results in a phase difference between the current and the voltage waveform. So during each cycle, extra energy addition to any energy consumed in the load is temporarily stored, then the same stored energy returned to the power grid. That power is called as a reactive power. Now we shall see what is the lagging, leading and unity power factor. Basically, power factor is the measure of the degree to which a given load matches that of a pure resistance. So power factor is equal to 1 if load appears as a pure resistive load, and if power factor is equal to 0, load will be as a pure inductive or a capacitive. For if the load is a combination of both resistive and inductive, then the power factor will be between 0 and 1 and it will be the lagging power factor. If the load is combination of resistive and capacitive, then the power factor will be between 0 to 1 and it will be leading. So moving on, one can relate the various components of AC power by using a power triangle. This is a power triangle. Real power on horizontal axis, reactive power, and the sum is the apparent power, is phi. So what will be the value of cos phi? It will be the ratio of real power by apparent power. So that is what the power factor is. So we can also define the power factor as if phi is the phase angle between voltage and the current, then the power factor is equal to cosine of the angle, that is cos phi triangle. Now we will see the real power, reactive power, and apparent power. Active power is basically the actual power dissipated or consumed. It does not produce any phase shift, and this power can be denoted by letter P, while the units are as watt. As far as the reactive power is concerned, it is imaginary power in a capacitive or inductive load. It can be denoted as a letter Q and measured in VAR, VAR. The reactive power exists in the system when voltage and current in a AC circuit are not in phase. As we have discussed in our previous slides, capacitors and inductors store energy, and this can be revived from the device later on. Hence, this form of the energy is neither lost nor gained, yet affect the system performance. So, reactive power plays a role in the power system. Now, as far as the apparent power is concerned, it is the complex sum of the real and reactive power. It is calculated. It is the calculated value of the power independent of the type and the load. Similarly, this power can be denoted as a letter S, and the units are VA. Basically, it is the similar to the power in DC circuit. That is, it is the arithmetic product of the voltage and current. Now we will see the significance, or we can say the importance of the power factor. If a high power factor is desirable in a power delivery system to reduce losses and improve the voltage regulation at load. This is to improve the stability and efficiency of a network. So, for a constant load at a constant voltage, the current drained from the source is inversely proportional to the power factor. We can say the power factor, we can say the real power is equal to P is equal to VI into cos phi. If we take the value of cos phi, the cos phi will be equal to P divided by voltage into current. As we said, power and voltage are constant, then the cos phi, that is the power factor, is inversely proportional to the current. We can say increase in current increase directly impacts the cost of power generation as a current, and this also increases the transmission losses, because we know therefore a huge penalties on consumers who have a power factor below or defined, or we can say a certain level. So this is very important to maintain a power factor at a certain level for effective utilization of the power. The last topic is about how to improve power factor. Power factor correction brings the power factor of an AC power circuit closer to 1, or we can say to unity, by supplying or observing. uh, Power factor correction brings the power factor of an AC power circuit to closer to unity by supplying or observing reactive power. Power factor can be improved by the following ways. by installing capacitor bank, by using synchronous condensers, or by using phase advan by using phase advancers. So this is all from today's discussion. If this video is informative for you, then I would like to request you to please subscribe my channel for more informative videos in future. You can also ask any question in comment. Your question will be answered accordingly. Thank you.